Okay, so previously we were doing chapter number I guess 17, 16, and that is counting and choosing. So basically we want to discuss this binomial coefficients, binomial theorem, multinomial coefficients, and multinomial theorem. And in the previous lecture of this theorem, this chapter, we have discussed the rule of multiplication principle. So we have given a theorem and then defined it, and then we have explained it by some example. Then we have given another proposition which says that if you have a set consisting of n elements, the number of different arrangements of the elements of S in order is n factorial, and we have proved it also. Now we will talk about binomial coefficients. Right? So let's define them. Definition. So let n be a positive integer and r an integer such that zero is less than or equal to r and r is less than or equal to n, and define nr and choose r called and choose r to be the number of all element subsets of 1 to up to n. Okay, so this is called n choose r to be the number of r element subsets of this set. Okay, so for example, the two element subset of the set 1, 2, 3, 4 subsets of this set are going to be 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, and 3, 4. And so we can write 4 choose r is nothing but 6. Now, it's not easy and it's very lengthy to write this number and like find the number of subsets and then write this number. So what can we do? We can give a proposition 16.2 which says that we have n choose r is equal to n factorial over r factorial n minus r factorial. Okay, so we can prove this proposition. So let's prove it. So we say let S be a set containing n elements and count the arrangements of S in order as follows. Count the arrangements of S in order as follows. And stage one is choose an R element subset T of S. There are n choose R choices. Stage two is choose an arrangement of T by proposition 16.1. There are R factorial choices. Okay. Then stage three is choose an arrangement of the remaining n minus r elements of the set S, and there are n minus r factorial choices. Then by the multiplication principle, the total number of arrangements of the set S is equal to the product of these three numbers. Hence, by proposition 16.1, we have n factorial is nothing but n r cross r factorial cross n minus r factorial, and it follows the result because this is nothing but n factorial over r factorial n minus r factorial multiply r factorial multiply n minus r factorial. So these two will be cancelled out and you are remaining with n factorial, which proves the result. Okay. Another way of expressing the conclusion of proposition 16.2 is that we can write and choose r as n into n minus 1 n minus r plus 1 divided by r into r minus 1 up to 2 point r 2 dot r. Okay, there are some identities, so you can say some useful particular cases. Of this r, so you can say n choose 0 is similar to n choose n, which is 1, because there is only one 0 element and one n element subset of S factorial. Because there is only one 0 element and one n element subset of the set S. And we can say that n choose 1 is n, because there are n element subsets of S, because there are n one element subsets of S. Okay, now n choose 2 is going to be n into n minus 1 over 2. Similarly, n choose 3 is going to be n into n minus 1 into n minus 2 over 6, and so on. So example, Liebeck has taught the same course for at least for the last 16 years. And tells their 3 jokes each year. So you can say Liebeck has taught the same course for the last 16 years and tells 3 jokes each year. He never tells the same set of 3 jokes twice. At least how many jokes does Lee back? No. When will he have to tell a new one? When will he have to tell a new one? 2 questions. Okay. Answer. Suppose Liebeck knows n jokes. Then n choose 3 is 16. N choose 3 must be at least 16, since 5 choose 3 is 10 and 6 choose 3 is 20. It follows that n is greater than or equal to 6. So Liebeck knows it least 6 jokes and will have to tell a 7th in 5 years time. Perfect. Now the numbers and choose R are known as binomial coefficients. This is because of the famous theorem which we will give now. (16.2). Name is Binomial Theorem. Okay. Says that let n be a positive integer and a comma b be real numbers, then a plus b power n is r is 0 to n, some r 0 to n, and choose r, a power n minus r, b power r. If you express it more, you can write it as a power n plus n into a power n minus 1 b plus n choose 2 a power n minus 2 b square plus dash dash plus n choose r, a power n minus r b power r plus and choose n minus 1 a power 1 b power n minus 1 plus b power n. Right. Let's give the proof. Consider we can write a plus b power n is a product of n brackets. Okay. When we multiply this out to get a term, a power n minus r, b power r, we choose the b from r. From r of the brackets and the a from the other n minus r brackets. So the number of ways of getting a power n minus r, b power r is the number of ways of choosing r brackets from n, and hence is n choose r. So in other words, the coefficient of a power n minus r, b power r is n choose r. The theorem follows from there. Perfect. So let's do something tricky and interesting. So let's write some of the few cases of binomial theorem and observe them. Here are the first few cases of binomial theorem. So let's say a plus b power 0 is 1. A plus b power 1 is a plus b. A plus b power 2 is a square plus 2ab plus b square. Very good. A plus b power 3 is a cube plus 3a square b plus 3ab square plus b cube. A plus b power 4 is a power 4 plus 4 a cube b plus 6a square b cube, not b square plus 4a b cube plus b power 4. Perfect. The last one, a plus b power 5, a power 5 plus 5 a power 4b plus 10 a cube b square plus 10 a square b cube plus 5a b power 4 plus b power 5. Okay. Now, here are one or two patterns to observe about this. First, each expression is symmetrical about the center. This is due to the fact obvious from proposition 6.2 that we know this that n choose r is actually equals to n choose n minus r. For example, we have 5 choose 2 is similar to 5 choose 3, which is 10. Okay. Rather, less obvious is the fact that if we write down the coefficients in the above expression in the following way, known as Pascal's triangle. Now, if we write down the coefficients in the above expressions, in the following way, known as Pascal's triangle. So let's write that those coefficients. Okay, so we are saying 1, 1, 1, 1, 1, 6. One more. Then we have 1 here. And we have 2, 1. Then we have 3, 3, 1. Then we have 4, 6, 4, 1. Then we have 5, 10, 10, 5, 1. Perfect. Then you can see that each entry is the sum of the above it and the one to the left of that. You can see that each entry is the sum of the one above it, and the one to the left of that. Let's break that. So let's say we have this one. So we start from here. Now this has one only, nothing on the left. And this has nothing on the above, but only on the left. Similarly, all these have nothing on the left, just the above, so they are only one. Now, 2 is sum of these two. 3 is sum of these three. 4 is sum of these two. And 5 is sum of these. Now, 3. Okay. If you talk about, wait. We can say something, not the sum of this, but that 2 is sum of these two. 2 is sum of these two. 3 is sum of these two. And 4 is sum of these two. So your 2 goes here, 3 goes here, 4 is sum of these two, then 5 is sum of these two, and then 10 is sum of these two, 6 is sum of these two. So you can go for that. And similarly, sum of these two, and then 5 is sum of these two. 1 is only there, something like that. Okay, perfect. This is explained by the equality. So you can write it, this is explained by the equality that n plus 1 choose R is nothing but n choose R plus n choose R minus 1, which you are asked to prove in the exercise before. Okay, now putting so let's put A is 1 and B is X in the expression in the binomial theorem. We will have the following proposition. So we say proposition 16.3 that for any positive integer n, 1 plus x power n is nothing but r 0 to n, and choose r x power r. Similarly, putting x is plus minus 1 in this, we get an interesting equality. We get that sum from 0 to n of this n to r, n choose r, is nothing but 2 power n, where sum from r0 to n of minus 1 power r, and choose r, is 0. Perfect. We'll end this here, and then we'll talk about multinomial coefficients in the next lecture.